Well, hi everybody. We're going to start off today's lesson with a story. And this story is about a monk. And this monk is going to take off on a journey at dawn. And he's going to climb a mountain. He's going to follow a path and climb a mountain. And he's going to get to the top of the mountain at dusk. And then he's going to stay there and camp for the night. And the next morning, he gets up and he leaves to come back down the mountain at dawn again. And he walks down the path and he gets back to the bottom of the path at dusk. And he realizes that somewhere along the way, he had been in the same place at the same time on both days. And so he had experienced deja vu. And so today we're going to take a look at the math behind that feeling of deja vu. So let's take a look at his graph, his picture, and see if we can't make sense of such a bold statement about this deja vu statement. So I'll make a little graph this way, graph this way. We'll have both days going here. And then I'll superimpose it onto each other. So we'll do 3 of them. Alright, so on the way to the top of the mountain, he left at dawn and he arrived at dusk. So we'll just let my marker there. We'll let this beginning point be the bottom of the hill, and this will be the top of the hill. So he, meandered around there and just finally got to the top of the hill at dusk. So this was the first day. And then in the second day, he started at the top at dawn. Let's see if I can write dusk a little bit better over here. Okay, that's better. And he started at the top the next day, and then he just meandered down and arrived back to the bottom at dusk. So let's take a look at these two graphs right on top of each other. So day 1, he goes up to the top there, and then day 2, he comes back down to the bottom here. And this point right here has a time, some point during the day, and also a place, some place going up the hill. And at that point where those graphs cross, he is at the same place, the same position, and at the same time of the day. So that's why he got that deja vu feeling. And this is guaranteed by something called the intermediate value theorem, which says that if you have a continuous function, there is no way to connect two dots without touching every single y value between those two y values. So let's take a look at the definition first, and then we'll do a couple of examples. So here's what the intermediate value theorem says. First of all, we've got to have a continuous function on a closed interval, and we've talked about continuity, so you should know what that means. And k is any number between f of a and f of b. Keep in mind these are going to be y values. K is a y value, f of a is a y value, f of b is also a y value. Get my spelling. Then there is at least one number c in this interval. These are x values, such that f of c equals k. Let's draw this picture and let me show you what this is saying. Let me get my line here. Get back to my marker. Okay, so let's see if we can figure this out. I've got a x value of a, and I've got an x value of b. And I've got a y value of f of a, and then I have a y value f of b. So here's what the intermediate value theorem is saying. There is no way to connect this dot from f of a to f of b without touching every single y value between f of a and f of b. So this is saying that if I were to have some value k that is right here on the y-axis, and I'll go across the graph so you can believe me, there is no way to connect these two dots without crossing that line. And that there's some value c in here that is guaranteed for us to cross it. Now we could even cross that line more than once, but the intermediate value theorem says you have to hit this y value at least once. So let's take a look at some specific examples. By applying the intermediate value theorem, choose the interval over which x to the fifth equals 2x to the fourth plus 11 will have a solution. Now, this is typically used to find roots. That's places where the pretty picture crosses the x-axis, or 0. So let's set this equal to 0, and let me show you how this can be useful. Let's find for this function x to the fifth minus 2x to the fourth minus 11, let's find f of 0 and f of 1. I'm going to try C here, and let's see if we can figure this out. If I plug in 0 for all of these x's, I get negative 11. And if I plug in 1 for these x's, I get 1 minus 2, which is negative 1, minus 11, I get negative 12. So what does this tell me for this graph of x to the fifth minus 2x to the fourth minus 11? Well, it doesn't tell me much. It tells me that at 0 it's down here at negative 11. And then at 1 it's down here at negative 12. So does the graph have to equal 0 in between these 2 points? No, because equaling 0 means crossing the x-axis. So it's not that one. Let's try E here. Let's try 2 and 3. Let's find f of 2, and let's also find f of 3. That's going to require me to do a little bit harder math. F of 2 is going to equal 2 to the fifth minus 2 times 2 to the fourth minus 11. 2 to the fifth is 32. 2 to the fourth is 16 times 2 is negative 32, and then minus 11. And if I do that math, 32 minus 32 is 0 minus 11. I get negative 11. Now what about f of 3? This is going to be 3 to the fifth minus 2 times 3 to the fourth minus 11. Now 3 to the fifth is 243. 3 to the fourth is 81. 81 times 2 is negative 162 minus 11. Now 243 minus 162, that's going to be 81. 81 minus 11 is 70. So what does that tell us? That tells us that at 2, the graph is down here at a negative 11, and at 3, the graph is way up here at 70. So what does that mean? Here, keep in mind, here is the x-axis where y is 0. That means that there must be an x-coordinate between 2 and 3 where I cross the x-axis, making this equal to 0. There's no way to connect these two dots without somehow crossing the x-axis. That means that my root is somewhere between 2 and 3. Let's do another example. I've got f is continuous on 2 to 4, and I've got the value shown. The equation f of x equals 3 must have at least 2 solutions on the interval from 2 to 4 for k equals blah. Well, that's pretty wordy. Let's see if we can't graph what we know so far. I've got the point 2, 5. 1, 2, 1, 2, 3, 4, 5. And then I've got the point 3 comma something, 3 comma k. That's what I'm going to find. So I can't graph that yet, so I don't know what k is. And then I've got the point 4, 9. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, it says the equation f of x equals 3. This is an equation of a horizontal line. And the graph of y equals 3 is the horizontal line, let me actually do it here, right here at 3. So there's a graph of y equals 3. I guess I could have extended that. There. Not perfect, but I did it. So there's a graph y equals 3. And the question says, the equation f of x equals 3 must have at least 2 solutions. This means 2 intersection points. For graphs to have solutions, they cross each other. And so from 2 to 4, what is the value of k? Where do I have to put that y value right here to make sure that when I'm connecting these two dots that I cross this line twice? Well, let's just see here. What if I allowed k to be 3? If I let k be 3, then that would mean I was at the ordered pair 1, 2, 3, up 1, 2, 3, and I'm right here. Does the intermediate value theorem guarantee that I would have to cross this or intersect this line twice to connect these dots? And the answer to that is no, because I could just go like this and only intersect it once. So that does not work. So we're going to take that off. Let's try another one. What about if k was 4? What about if this y value was 4? So over here at 3, up here to 4. Am I guaranteed to, as I'm connecting these dots, am I guaranteed to cross this line y equals 3 at least twice? The answer to that is obviously not. I could just come down like here and connect these 3 dots without ever touching that line y equals 3. So that doesn't work either. All right, what about the y value of 2? So what if I made my k 2? So I was over here at 1, 2, 3, 2. Oh, I need to erase this other dot here too, don't I? Erase that one. Okay, so if k were 2, then would this guarantee that I would have to cross the line y equals 3 twice? Well, this definitely does. If it's continuous, I would have to cross the line to get here once, and then I would also have to cross the line again to get back up here. So there are 2 solutions to the line, to the on 2 to 4. There's 2 solutions for where that graph crosses the line y equals 3. Now does this mean it has to do it exactly twice? I mean, the graph could have, let me erase this and get back here to my marker. I want to show you some. The intermediate value theorem doesn't say how many times it crosses. 2, 4, 5, and then 4, 6, 7, 8, 9, and then we said 3, 2. The graph could have come down here once, gone back up, come back down, gone back up, and done this. It could have, crossed it 1, 2, 3, 4 times. So it doesn't tell you exactly how many times it's going to cross. It's just going to tell you how many times it has to cross at least. Okay, so that is, let's do one last example, and the question would be, does f of x equal x cubed? Do all cubics cross the x-axis? Well, the answer to that we can come from something we learned a long time ago, and that's with end behavior. So if you remember that all things that have an odd degree either go down to the left and then up to the right, or they go up to the left and then down to the right. That's the only 2 choices for a cubic. And of course, polynomials are continuous everywhere. So we know we're dealing with a continuous function. So no matter what the cubic graph, does it have to cross the x-axis? And the answer to that is yes, because of end behavior. Because it either goes up to the left and down to the right, or down to the left and up to the right, and somewhere in there it's going to definitely cross the x-axis. That's another example of a question you'll be facing tomorrow. So anyway, that's it, and I'll see you guys then.